Okay. So also live stream running. We'll usually be a few minutes late for setup and allow people to travel from other rooms. So again, the announcement, make sure you're signed up on Slido for the questions. Make sure you're signed up on CampusWire for the module. And I suppose you also want to know the attendance code. So let's switch to that. Before we get started, I have a few quick announcements that I think is useful for everyone to hear. Number one, in terms of posting and direct messaging on CampusWire, if there's any chance things are interesting or important for other students to hear, consider posting them on CampusWire as opposed to direct message or email. All you'll get from me is usually, can you please post it anyways? So it's quicker if you just post it straight away. Unless it's something that only concerns you and you alone, then obviously direct message or email is fine. A few people, I think I posted this as well, a few people had clashes on their timetable. If that happens, I cannot change it anyways. If you want to officially swap tutorial sessions for this module or any others, go to the student experience team, the ground floor student office in the Ashton building. They can try to swap you to a different session to avoid the clashes. Sometimes it's inevitable. In general, the lectures are recorded and tutorials are not, so rather go to the tutorials if in doubt. But we'll try to avoid clashes where possible. Ben says for the tutorial for this class, he's happy if people attend another session than the one they're officially scheduled for, if and so long as the rooms are not too full, in which case you might get asked to leave and attend the session you're scheduled for. So in principle, we're flexible on that front, but it might be better for you to get it switched on the official timetable. Then it shows at the right slot and so on. The last announcement is about past exam papers, because several people asked. And I pointed you to this, but it doesn't seem to be obvious to everyone. So you should all be enrolled on this Canvas module called the Computer Science All Students course, which has lots of important information, not just past exam papers. So make sure you're checking out what's up there. The assessment-related information is where you want to go for exam papers. And here's where can I find past exam papers, which is a fun question because the answer is click on this question. And there you have a few exam papers. There's one very old one for 526 up here, which is here. So this module used to be a semester 2 module in the past. But if you search for the number, you will find it. There should also be a more recent one, a more recent old exam from when I was doing the module. And as you can see, I should have just gone back. As you can see, they promised to upload some exam papers from last year at some point. So keep an eye on this. But that's in general where you find these. Last point before we get started was the prior knowledge survey. I will not discuss individual questions here in detail. That costs us too much time, and they're also not so important. A few general remarks. 2/3 of this cohort are from the Advanced Computer Science course. And a bit like, well, a quarter is in the conversion masters, and then there's a few others. The largest other group is big data, but we also have a few other courses present. I'll leave that for you to read. Sure, take a seat. So the basic math questions were not a problem, and Python semantics, many also found that okay. Computing limits, quite a few people weren't sure, or here the majority of people didn't know. So that's something I'll keep an eye on. It's not so relevant for this module because for large parts of it, we'll come to it. There's a few simple rules that will suffice. We'll talk about this in more detail today and tomorrow, what ADTs are, abstract data types. And then again, the combinatorics, many people knew. And OK, this was meanly posed. Same for this one with the full alphabet as answers. You should be able to see the evaluation, and I think you can also see the questions if you pretend to edit your answers, which again, this is just for information. No need to edit your answers. Any questions from your side on organizational matters? If anything's up on at any point during the lecture, then also please use Slido the questions to reach me. And I wanted to check. OK, we seem to have a few people joining remotely. So also, if the connection breaks down or the audio isn't good, that's a way to let me know. Shall we get started with the actual topics and content? Good. Let's do it. Welcome back to COMP526. We'll start a new unit today on machines and models, which will be about representing mathematically what we mean when we talk about algorithms and data structures and their performance. My goal for you from this unit is to take some fundamental understanding that goes a bit beyond just what you do for programming. I want you to understand what the difference is between an analysis and running time. Then the important notions that we have for modeling different parts of what we do in algorithms. We have models for the input, we have models for the machines, and we have models for the cost of an algorithm for an execution. And we'll touch on the main notion that people use in computer science for expressing running time statements, the asymptotic notation. Again, some of these things you will have seen in previous modules if you've done an undergrad in computer science, and some are also maybe used even outside of computer science now. But we'll go from first principles at a faster pace than you would do this in an undergrad course. But everything you need to know for this module is in there. It's just coming at a relatively quick succession. So this module is about algorithms. So we should have a little conversation what an algorithm is. What I'll give you is a definition that still has some vagueness in it. So for us, an algorithm is basically a sequence of instructions. And you can say the metaphor is a cooking recipe. So it should tell you at each point in time what to do. Now, the difference to a recipe is, as you may know, if you're a hobby cook, sometimes the instructions are not so clear. At least if you're not an expert cook, there may be some steps that are not self-explanatory. That's something we'll have to avoid for algorithms. Algorithms have to be explained in a simple language that's understandable even for stupid computers that have no common sense and no experience. So they will be expressed in some formal language. So what we mean by this is it has to be mechanically executable. And for example, that can be a Python program or any other programming language. And we would distinguish this probably from a natural language description that maybe some large language model can translate to some code. But in this case, we don't have any guarantees that it does the right thing. We just hope it does something sensible. For an algorithm, we want precise instructions. A more subtle point is it should be a finite description. You have to be able to write it down. It's maybe obvious to state, but if you explain an algorithm on an abstract level, it sometimes is natural to specify things that if you spell them out for a computer, it would need an infinite number of cases, and that's not allowed. And then the last bit is to distinguish an algorithm from a concrete program. Not every program is an algorithm, and that's the vague bit. We want algorithms to solve an entire problem or entire class of problems, as opposed to just computing a specific thing. So maybe in terms of this example, if you're just computing the sum of two numbers, that would be just some program. If you have a method that computes the sum of any two numbers, that's an algorithm. Of course, that's a very simple program, and we'll look at a few more interesting problems, but that's the gist of it. We'll usually abstract it like this, as you will have seen. So there's some input going into the algorithm, then it does something, and it produces some output. That's usually our model for thinking of these. Of course, output could mean it modifies a piece of memory that you provided it with. That's also fine. And to illustrate this, an example of an algorithm could be the famous bubble sort that we all know is not such a great sorting algorithm. It's not so fast, but it is an algorithm. And it describes an idea that roughly tells you how to sort. But it's not a specific program. When you say bubble sort, there's many different ways how you can implement it. It depends on the programming language, how it looks in detail. And there's slight variations in bubble sort. I don't want to get too much into this if you haven't seen it in detail, but if you do bubble sort, you continuously exchange two neighboring elements if they're out of order, and you do this from left to right until you're one pass through the data, and then you do it over again. Now, one version of bubble sort, just cook until done. Do this until you've never made any exchanges. So you do one more pass over the data where you don't do any exchange, and then you know you're done. Another option is to say, I don't want to do anything with checking. I'll just do n passes, and I know n passes are enough if n is the input. That's two slightly different variations, but both would be called bubble sort. It's just the difference is too small. So you would call it both bubble sort, but of course the programs look slightly different. So an algorithm for us often is a bit more abstract. It's the key essence of a recipe for computation. And I understand this is a bit of a vague point, but hopefully you will see many examples in the course, and then we'll recognize which ones are coherent abstractions that might deserve a name. So much for algorithms. Don't want to lose track of Slido. The second part we'll be concerned with in this module are data structures. They're often called hand-in-hand algorithms and data structures, and that's for the following reason, that they're very related. A data structure is two things. First of all, it's some way of representing a piece of data in computer memory. And what is data? That depends, and we'll see more examples in the next unit. So I'll leave it a bit abstract here. But it tells you exactly, a data structure tells you exactly how to represent the data you're storing in computer memory in bits and bytes. And the second part is it has algorithms that tell you how to do something with the data in the representation that you have it. And usually we distinguish, it's either something queries, just ask a question about the data, and updates change it, but you can have various mixtures. And an example you may have seen if you've done that you must have seen if you've done in CS undergrad, is a binary search tree. But we'll see other examples. So much for the broad introduction. In the next section, we want to look a little bit about the specific analysis. So that's where the mathematical modeling comes in again. So far, it's been a bit wishy-washy and vague, and the terms algorithms and data structures need to be a bit vague. But what's coming here is trying to make things very precise. The whole motivation why we do this comes from the fact that if you have a certain algorithmic problem, there are usually many ways to solve it. And the question is which algorithm or which data structure is best suited. So you need a way to tell good algorithms or data structures from others, not so good ones. And I claimed bubble sort is not good, so I should have some way to quantify that. Usually we mean fast, but we might also mean space usage. Depending on the circumstances, one or the other is more important. We'll briefly look into parallel algorithms where time is again a bit more complicated, but we'll come back to that later. So what is algorithm analysis? It's a methodology that allows you to compare algorithms by measuring how well they work, and also to predict how fast they are. And how accurate that is possible depends a bit on what you define next as the model. But that's the goal. We want a way to compare different algorithms so that we can quantify their cost and find the one that has the better trade-off for us. And if we pick a specific algorithm, it's useful to be able to do at least a back-of-the-envelope calculation how fast it will be or how much memory it will take. That's the feasibility check. Now, one option to analyze algorithms would be implement them and just run them and see what happens. And sometimes that's the only option you have, or it's the fastest way to go. That can be possible. The problem with that is that it is a bit limited in what you can make as statements. You can run things on a concrete computer and you will get numbers for that concrete computer, but it's not clear if you can do if you can make predictions for other machines. Also, you have to run it on some concrete input, some data, and it's not clear if what you find generalizes to other kinds of scenarios. And lastly, you have to implement it. So if you think back when I said an algorithm is more of the essential idea of some computational recipe. If you decide you implement bubble sort one way, and that turns out to be bad, you never quite know if there's maybe a slightly better way to implement it that would do much better. And that's not so satisfying. So in particular, remember I had this comic about the philosophy of the module. We're after the universal truths of algorithmics. And all of this sounds like not so universal. So instead, what we like to do is have some way of comparing algorithms that survives the current hardware so that it can make statements that are a bit more eternal universal. We'll still have a model of reality that we might need to validate. Okay. Is that okay? Still works. I feel I was a bit too loud earlier. Is it okay now? Okay, I'm not. Okay. Aha. Right. So I hope the plug is in now again. Interesting. Is the volume okay so, or like this, or too loud, too low? You can hear fine in the first row, but the guys in the back have to tell me. Looks good? All right. Okay, sorry for that. So what this is all about is that we need a precise model to be able to do that. If we just rely on the current computers that we have, we'll only be able to say something about those. And so we need to abstract from the concrete machines we have if we want a statement that transpires beyond the current machines. Is maybe self-evident. And we'll come to how to model machines. What we'll also need is a model for the data we work on. Because again, we can try to run it on concrete inputs, but we often want something that is more generic. And there are 3 different models that people have used in algorithm analysis a lot. And you'll be familiar with those, or it's very intuitive. The worst case performance means take the worst possible input. And that's a bit pessimistic, but if you have a guarantee that your algorithm in the worst case is good enough, it'll be good enough in any case. Best case means take an optimistic point of view, take the best. That's usually just useful to rule out algorithms. If already the best case is poor, then maybe it's not worthwhile exploring that algorithm. An average case tries to interpolate between the extremes, and we'll come back to that in the context of sorting. So here you're just assuming there's some random distribution over inputs, and you're computing an expected value of the cost. Now these sound like you take all possible inputs and take the worst of them. Usually that's not well defined because we allow an infinite number of inputs. If the algorithm is for an abstract problem like add 2 numbers, the 2 numbers could be arbitrarily big. And it's unreasonable to expect that the cost of an algorithm does not depend on how big the input is. So instead we'll group inputs by the same size. All inputs of size n are one group, and then all these measures above pick from just a fixed size. So worst case would be the worst possible input with a given size, or the best possible input of a given size. So for each of these 3 different data models, we would get a function of n for the performance. It's not just a single number, it's a function that tells you for each input size how long would the algorithm take. In the next section, I want to show you the standard model for computers that we use in algorithms these days. That's the random access machine. And this is I saved this for the last part because it's a bit more intricate, and it has a little twist to it that we'll come to. And to motivate that, I'd like to ask you this question without saying too much. I've had 114 people vote on the attendance code earlier. It looks like you're more than 114. Not in age. Let's wait until we have 100 people voted, and then '98. All right. One more. Good. There's the results that people voted. And let me briefly discuss this a bit. They're really different answers that all make sense, depending on some assumptions that you make. So it could be that it takes constant time to add two numbers. On our so taking the concrete model I'll show you in a moment aside, on your computers that you have with you, it takes constant time if the numbers have at most 64 bits. Then it's quite guaranteed. Well, almost all computers these days have 64-bit architectures. So it fits in one word, and then there's one machine instruction that adds two numbers, bam, done. And it can do, I don't know, a few billion per second of these, right? Constant for us just means it doesn't depend on the input size. Now that's a little cheating, because if the numbers are big, it does take more time. And so the algorithmically more sensible answer is C. If the numbers keep growing, then it will be time proportional to the length of the numbers in bits. So I would say this is more correct, right? But if you write a program that always just uses numbers with at most 64 bits, the first answer is what you'll see. And OK, the last is of course correct, but we'll try to fix that. Maybe a quick comment. Why is it proportional to D? Well, you do the primary school method. You start with the last digit. You add those two digits up. There may be a carry digit, so you have 3 digits in the next step, but that's all. So you add these 3. Then you get the next digit. So in each step, you get 1 digit of the result produced. And you have D digits in total to process. Maybe it's D plus 1 in the end. But that should be it. All right. So the machine model is really important because it determines how algorithms look like. It tells you what algorithms are possible and in what kind of language they are expressed. And it also defines usually what the cost of an execution is. And because it defines all these things, there's a few trade-offs that are tricky in general to get right. It should be detailed and powerful enough to reflect what current machines can do. For example, what I just said, if you have numbers with at most 64 bits, it's very fast to add them. Whereas if you have much longer numbers, it takes more time. Somehow the model should reflect that. It should also be abstract enough to not change every year. Otherwise, gone our eternal truths. But then also, we would like it to be simple enough to analyze it mathematically. So this first point and the last point are in clear opposition. So sometimes you may need a compromise and can't get all 3. Here's the solution that algorithms research has essentially settled on. It's a bit of a mouthful, but don't get intimidated. It's just trying to define all that a computer can do in one slide, and so it has to go through a few different things. There's a book which is listed on the module page. So little digression, little aside. You know the module has a module website, which is linked on Canvas, but is living outside of Canvas on my personal website. And the module page has subpages for all the units. And unit 1 has the slides from today. We'll have the videos from today after some point. And also has a list of further reading and sources at the bottom. And there you'll find a link to this book. It's in the library in some form. Most books you can borrow from the library in electronic form, which is probably most convenient, but they also have some print copies. So the definition here is in much more detail described in this book, but I'll try to give you the short version. Our computers, the random access machines at least, have one big array of memory. It's essentially unlimited. You can use as much as you need. I'll comment on that in a second, why that Sounds a bit weird, right? But why that might be okay. That's memory where you can store data. But to work with the data, you have to copy it to registers. And there you have a fixed number. And that number is not usually very important, so I'm generous. I allow you to tell me how many you want, but it should be somewhat reasonable, maybe a few hundred at most. Definitely independent of the input size. So you have to write a program that fixes the number of registers without knowing how big the input is that you work on. The memory cells themselves, they can each contain a number. And that number is an integer with W bits. And that's where things get a bit tricky in a way. We have this second parameter, W, that is part of the machine model. So you have to tell how large that is. And most current computers have essentially 64. Not too long ago, it was 32. If you're strict, then many of the computers actually have more than 64 because they have these SIMD instructions, single instruction, multiple data, where you can work on longer words, up to 265 at least, maybe some graphic cards even more. And they split this. It's treated as a vector where you can do vector-wise operations. So in a way, even 64 is playing it safe. But to come back to the formal model, each memory cell contains a number with W bits. So that's an integer between 0 and 2 to the W minus 1. And now the clue is that this word size is allowed to depend on the input size. That's a really weird concept. The machine grows with the input. And a typical assumption is that by and large, W is logarithmic in the input size. A quick motivation for why that roughly is if you write down the input in an array, you want to at least have a way to say, I want the ith bit in the input. And that number I should fit in one word, because that's mostly possible in computers. The second reason is you usually want to be able to use addresses to memory in operations. For example, you can add up 2 addresses in computer memory. And so to be able to do that, they should fit in one word. So this is a somewhat natural assumption, but maybe it looks really weird if you see it the first time. These two things, that the input is essentially unbounded and that the word size grows with the input, might look really strange. But if you look back historically, if you don't treat this as a model for one laptop on your desk, but for all of the computers over the history of computers, it makes a little more sense. The word size has kept growing over time. It started with single-digit number of bits, and then quickly went to 32, and now we're at 64, and even going beyond that with these SIMD instructions. And at the same time, the data that the computers worked on was also growing, and roughly in that relation, exponential growth. So don't treat it as a weirdness of the model that it seems to grow with the input. Imagine rather, if you want a bigger input to be solved, you have to build the machine up. You have to add more memory, and you have to increase the word size accordingly. Basically, any other way to define the model gives you other paradoxes for the theory that are not nice. All right, so I talked a lot about what the memory is like, how big it is, and how many bits you have in each memory cell. I will briefly talk about the instructions of the computer, but that's the slightly less important part. You have more leeway on this. But to be concrete, our computers here, the random access machines, can do basically 3 different things. One is they can load and store memory from data from memory. So you can get what's in a certain cell in memory and store it in a register. And the address is given by another register. So you can use indirect addressing. And you can do that for reading and writing. Then you can do all sorts of standard arithmetic on registers. So you can add 2 numbers, subtract, multiply, integer division, and integer modulo. And you can also do the C-style bitwise operations. I called them C-style because C popularized them back then, but most programming languages have operators for that. The same operators are used in Java and C# and so on. And Python has some way to express them as well. So you can, for example, take two numbers and do the bitwise AND. Treat the numbers as binary strings and do the AND of each digit and a few other related ones. These won't be so relevant for this module, but I wanted to list them to be complete. And the third thing you can do is jumps and conditional jumps in your program. That's to do logic in the program. So you can say jump back to line so-and-so, and you can say only do that jump if a register is 0 or something like that. So here again, you can compare two registers. We don't necessarily care about the fine detail here. That's the three types of things you can do. That's very similar to most. If you've done some undergrad in computer science, you will probably have done some assembly language, where you've built some, you've at least conceptually built a processor. And that's the kind of operations they support. So this is very close to the silicon that we actually use, but it's a bit abstracted from some details. The cost in the model, how long does a program take? In this model is assuming it's exactly the number of executed instructions. So again, for the experts, I'll point out that accessing memory here is assumed to take these kind of instructions. They take constant time, and they are as fast as doing arithmetic. That's often not true in reality, but as a first order approximation, that's what we assume here. Any questions on that model for now? I know it's been a lot of info, maybe. Because it's very, very low level. I said it's close to silicon style, what actual processors have as operations. It's very inconvenient to write any complicated algorithm in that level of detail. So we'll usually allow ourselves to do something that's closer to Python code. And you either have seen a compiler lecture, or you have to take my word for it that it's a solved problem how to translate from this more high-level description, if it's precise like Python, down to what I've just shown you. That's an automated process. That's what compilers can do. And they're usually even smart about it to make some optimizations along the way. So we'll ignore that step. For us, algorithms will live at a slightly higher level. But we'll know that if needed, we can go back to this slightly lower detailed level to measure the performance. Because we allow ourselves to work with this more abstract pseudocode, what we'll usually do is count dominant operations. So we don't count all instructions in the RAM program, because that would need us to write down exactly the program that we want to analyze. There's a famous theoretical computer scientist, Donald Knuth, who has done exactly that in his books, The Art of Computer Programming. Maybe some of you know the book. Many know the book, but haven't ever read parts of it. He does exactly that. He goes for all algorithms down to a level of the RAM and counts all the instructions precisely. It's doable, but it's painful. So most people abstract a bit from that and count dominant operations. So specific points in the program that will be proportional to the total cost if we count those. Here's a few things that we allow ourselves in the pseudocode. Instead of just doing conditional branches, we allow ourselves the usual kind of loop constructions that you would have in Python and other languages. We use variable names instead of registers with numbers. Maybe that's obvious, but yeah. If you work with assembly, you'll have to deal with that. And we'll also make another assumption that I'll talk about in a second. Again, my point about presenting this detailed model is twofold. One is I want to assure you that there is a level of detail that you can go down to if needed. And also, sometimes answering a question, for example, about sorting, we'll come back to that, requires that you specify what model you're working on. Even if your programs are abstract pseudocode, saying how fast an algorithm is might need to tell details about the model. So it's kind of something that's looming in the back, and we don't always go down all that level, but it's important to know how to resolve this. One last assumption that we use in our pseudocode, which is a bit of a bigger thing. It's again, if you've done an undergrad in computer science, maybe you've done a lecture on operating systems, and then again, you would know in detail how this works. Otherwise, take my word for it that it's a solved problem, but we'll just assume that this is already somehow done. If we're working on a RAM like I defined it, there's no such thing as structured memory. Memory is just this one giant array, and you can use as much of it as you want. We assume it's as long as you need it, but there's no structure to it. And it's super painful to write programs that way.
RAM architect doesn't deal with space complexity.
Sorry, say it again. The RAM
architect doesn't deal with space complexity.
Right, so the question is about the RAM model and space complexity. If you want to define the used space, you would take the furthest you access the memory. So you would assume you don't use, or there's the memory that you don't ever touch doesn't need to exist.
Let's say I have designed one algorithm. Let's say Fibonacci series, one with recursion and other with memoization. Now I have two systems. One follows the standard system prediction computer, and another one follows the RAM architecture. And the recursion approach I have put it in the RAM architect, and memoization algorithm I have put in 64 bits. So is there any point where efficient algorithm will cross the RAM architect algorithm? That is recursion, update, and memoization will cross.
Right, so the question was about comparing different, maybe I will have to take it offline and I have to ask you about the details. What we'll assume is that all algorithms are operating on the RAM. And I guess they all run on the same RAM with the same W. That can have consequences for the algorithms. Oh, the input, okay, I didn't talk about the details about the input. So the standard assumption is the input is initially written in the first n cells of the memory. And you can read and overwrite that. And at the end, you'll leave the output in the first few cells of memory. But you can change these conventions. That's not too essential. But yeah, you're right. I mean, there's already a full slide. There's some details that I left out. I tried to leave out those where no matter how you fill them, it doesn't change the model substantially. But yeah, maybe have a look at the book. They're a bit more rigorous about that part. Because you brought up recursion, recursive algorithms is another useful programming technique. Doesn't exist on what I defined on the RAM, right? Doesn't have any system stacks. It knows nothing about that. That's all something we'll assume that it exists without worrying too much about how it's done. So we'll assume that we have some sort of memory management built in. So we're able to just say, give me a free piece of memory of that size. That's similar to what you can do in C. Or you can allocate an array of a certain size with a certain type of objects. We'll also assume that you can allocate objects from some object-oriented program. If you have a class and you instantiate that, similar to what Python offers, we'll assume that that's also handled by this operating system that's running on this RAM without us touching it. If I talk about pointers in algorithms, that's basically just a number. It's an address of some memory cell. And that's what it is in reality too. But memory safe languages, I don't know if Python is memory safe with all the C extensions, probably not. But Java is a memory safe language that guarantees to you if you have a pointer, you're never gonna access a piece of memory that wasn't properly allocated. You don't get this buffer overflows in that sense, at least. So that sometimes they talk about references to make the distinction to a pointer that could be an arbitrary number in memory. For the algorithms, we won't make that distinction. A pointer and a reference is the same, and it's just a number of the address in memory. And yeah, as I said, recursive calls, all operating systems have a system stack where you can call functions recursively and so on, or non-recursively. We'll also assume that that exists. Okay? That's a bit of a slide for everyone who's seen some of this before. If not everything on that slide makes too much sense for you, don't worry too much. I just wanted to put this up so that those people who know about it know our assumptions on it. Right, time is racing, so maybe this is a good point to take our little break. So let's take a few minutes break. We continue at 4. I might take 5 more minutes, go till 35 in the end, but hopefully that's fine.
What's the code for that 10 minutes?
Let me start it on Slido again. Maybe other people need it too. Yeah. There it is. Can you see it now? It's 889691.
So I was wondering, compared to like say last year's cohort, how many people were in advanced computer science compared to like?
I think it was somewhat similar, but a bit more balanced. So the year before last year was almost half-half, and last year was a bit like this time. Definitely the majority advanced computer science.
Okay.
Now the number of, I think what happened is the number of advanced computer science students just went up further,
Okay.
and the others didn't drop. It's, but relatively speaking,
And
it's
like,
fewer.
so based on like your experience from the past, how did the like regular computer science people do? Did they hold
Yeah,
in there? They're
that's an interesting question. From the past performance was almost always the average among the conversion masters computer science was lower,
Of course, yeah.
but the variance was much higher.
Okay.
The best students most of the time came from the conversion masters.
Interesting.
Yeah, you can make from that many possible explanations, right?
Yeah.
The conversion master often attracts mature students or students who come back from industry. So they often bring some experience, even though they may not have a formal degree. it's not like they come with nothing, and they're often very motivated. At least the ones that do well.
Okay.
There's certainly a correlation there.
Yeah.
Yeah, the average it's not a big difference actually.
Okay.
So yeah, I would say they do fine.
I was just really surprised that 2/3 of people are from advanced computer science.
Yeah.
That's kind of eye-opening because
Yep.
I don't know. It's got me a little worried, but we'll see how it goes.
I don't think you have to be worried, but I think it's
Yeah.
useful to show the rest of the class what the composition is.
Yeah, no.
I think it's useful to see. Yeah.
Also, I saw that on your website, you had some like CS outreach stuff, and one of them was
Yep.
like intro to AI or something like that. How do you
Right, yeah.
like? How do you sign up for that? Like, is that something?
Oh,
that
it's
you're
no
still
module.
running?
It's just a collection of videos that you can
Oh,
watch online, and it's
Okay,
for
okay.
high school kids. I mean, there's intro to AI lectures that we do, but they go a bit deeper.
Uh-huh.
That one's you can have a look at it if you want.
Okay, I thought that was something I had to like like. I thought it was like a
No,
lecture
no,
like
it's
this.
no.
Okay. I see.
Yeah, it's something we developed during the pandemic.
Uh-huh.
So I'm running our school outreach, and so I started this during the pandemic, when all the schools were locked down and
Yeah.
nothing was really happening. So we thought, what can we do despite lockdowns to
Yeah.
get a few kids interested in computer science?
That was
So we developed that part.
Yeah, that was
Um,
like even before AI like really started catching on in terms of like.
Yeah, it was well before ChatGPT,
Yeah,
that's for
exactly,
sure. So
yeah.
large language models were not a big topic at
Exactly. Yeah,
around
but
then.
I think that's when it really started exploding. Like in terms of the
Yeah.
general public knowing about it and all that.
Oh yeah, it's yeah.
Am I
I guess
saying
it's fair to
something?
say. No. It's fair
Yeah.
to say. It's just depending on how your time scale is.
Yeah.
You can also say it's 10 years that deep learning took off, and it started with just the computer vision tasks.
Yeah.
Where previously this was just not working well. Like all the computer vision recognizing things in the image, it just didn't work. And then suddenly came these deep nets, convolutional neural nets with a few more layers.
It is.
Throw it on a bigger, beefier
So I don't know how it
graphics
was
card,
like
and
in the academic sense, right? But like, yeah, for someone like me, it just seems like all of a sudden, like overnight, it was just like such a big thing, and it didn't.
Yeah.
I don't know how it was in the academic sphere. If like people knew that something like that was like on the verge of coming up and stuff, but. Yeah,
I think almost everyone was surprised by ChatGPT.
Yeah, well, not even just
way it-
ChatGPT, but even the like image.
The language
like,
models.
like,
Oh well,
the
even
like
further back.
I forget what they're called, but like you know what I mean. Like I'm blanking on it right now, but the like art AI and all that kind of stuff. Like feels like that also just came out and just nowhere out of the blue.
Yeah, I think it's all. Nothing really happens overnight.
Yeah.
It's been cooking. In hindsight, I guess people say it's the combination of having faster hardware, especially graphics cards,
Yeah.
plus bigger data sets because you can use the web
Yeah.
to crowdsource
Yeah,
things,
and that's like
plus
controversial.
having the right algorithms ready at the time.
Okay.
Yeah. Large language models were a thing before ChatGPT. They just
yeah,
didn't
of
work
course,
so
of
well
course,
for
yeah.
conversation.
Um,
Yeah.
Yeah, I remember like playing around with like one or two before even ChatGPT.
Okay.
But it wasn't that good. So I wanted to ask one more thing about the. So okay. In terms of our lectures and what we're going to be tested on, is it going to be more so the stuff we're learning like right now, or is it going to be like a lot of the stuff from the last unit? Because I think I'm
I see.
understanding this unit a lot better than the last unit. I'm still.
Oh, by last
trying-
minute, unit zero.
Yeah. Like the more.
No, it's
Quantified statements or whatever they're called, like that kind of stuff. I'm still trying to get my understanding of
sure.
that better.
it's a mixture from different units,
Okay.
but it's only 1 out of 10, right? The unit zero. So usually, It will be a mixture. It's probably more on algorithms.
Okay.
I think that's overall more important. Right, guys? Time to move on. It's not a super long break, but I would rather let you go on time. I definitely want to go through this this last section of the Unit 1, and ideally also start the next one. We'll see how far we get. Shall we move on? Mics are fun, yeah. Good, fresh energy. I know it's been probably a long day, or has been for me, but I hope you have some focus left for the last part. There's a little bit of math definitions that I want to get to you, even though you often will be able to evade using them. But you should have seen them, because you need to know what to go to in case of doubt. In the last subsection, we'll talk about asymptotics and big O notations, because that's the way how computer scientists usually express statements about the efficiency of algorithms. And it's a useful approximation and just a piece of vocabulary that you need to know if you talk about algorithms to people. But instead of just showing, let's see how people are on this. I'll decide a bit on your answers, how quick to go. I don't want to bore people with things they already know, but also I don't want to go too fast for anyone who's not seen this much before. I'd love to see 100 votes, but I don't promise I'll wait for it no matter how long it takes. I'm a naturally impatient person. All right, I think that's good enough for seeing the rough picture. So we have a majority who knows this, but there's a substantial bar below with the I don't know big O at all. So let's have a look at it. And also for all the others, we'll come back to this, so no real explanation on this. I want to motivate a little bit why people use asymptotics before we dive into this. I'm not sure if that's very prominent or very obvious to anyone. The key thing why we use asymptotics is because the analysis of algorithms focus on large inputs. And the reason for doing that is if you're just concerned about small inputs, maybe there's a way to just list all the small inputs you need, or you do extra special cases for certain specific small inputs. So by focusing on large inputs, you can abstract away from special casing just a bunch of different cases. Focusing on large inputs then also simplifies the analysis, because certain cases, the certain boundary conditions don't play much of a role. We'll see examples for that. And sometimes you need to do this because one algorithm might be better for small things and then might go slower, and another one might be better for larger things. And generally, we think of the second algorithm as better. One way to think about this is, if I ask you, what's the fastest mode of transportation to get from point A to point B? It's really an unknowable question. If that is from here to the door, I'm probably faster than any mode of transportation that's just run, right? If you start laying down a train track, and in 5 years' time, or maybe, well, this is England, right? Maybe it will never be built, but let's not get political. So maybe you lay down this train track and you start your train, and it'll speed up and, well, stop right away. That's not a fast way of traveling. But asymptotically, if the distance is from here to London, I don't want to walk. And if you have a train, that's probably a good way to go. It's probably the fastest way to go, right? So that's why we focus on large inputs, or in this case, large distances. If you want to know what's with the parts where it matters, because overall the cost will grow with the input size. So the big inputs are those that you need to get right. For those you want to focus on, and you want to find the methods that are effective for those. Mathematically speaking, asymptotics means we look at an approximation of a function around infinity. That's an informal way to state it. And here's an example that maybe illustrates the point. This is one long function. It has a parameter n, and it tells you, for example, I've made this one up, but maybe there is an algorithm that has that running time. And it's a very long term. It looks complicated, and it's not really clear how fast it grows. You have to look very closely before you see it. Here's a graph of the function. You see it has these weird jumps at powers of 2 and all that nonsense. But there's a much simpler, much smaller function, a smaller term for a function that captures the growth of that function very well and is much simpler to write down and to understand. And in this case, this will have a precise meaning, this little tilde symbol. That's the kind of asymptotics we like. They take away the complication from a function and leave the important bits, but are easier to interpret. OK. I'll jump right into the formal definition of what the standard asymptotic notations should be defined like. Now, caveat, not everyone defines them like this, but they're mistaken. I've been working with these for many years, and that's the definition that causes least trouble. Trust me. And we can debate it offline if you want. First notation is the tilde that you've just seen. And we say two functions are asymptotically equivalent, or f is tilde g, exactly when their limit converges to 1. If you take if their quotient converges to 1. So you divide one function by the other and take the limit for n to infinity. OK? The more widely used relatives with this big O is defined somewhat similar, but it's a bit vague, a bit looser. So we say f is big O of g. If you take f and you divide it by g, and that quotient is bounded. So there's some number so that this quotient stays below that number for any n. At least for any n up to starting from some point, but you can alleviate that. There's a second definition. If you can read that, then fine. Otherwise, ignore it. It's the same. Note that big O should really be a set of functions, but it has become customary to write an equal sign where it should really be an element sign. You just have to deal with it. What it really means, if you write something like this, is what's here on the right. The quotient is bounded. That's the formal definition anyways. There are two variants. There's big omega, which is the opposite. F is in omega of g if g is in O of f. And there's big theta, which combines the two. So f is in theta of g if it's both in O of g and in omega of g. These are the formal definitions, and they're most useful for checking in details. There's one more less known cousin of these, the little o. F is in little o of g if the quotient goes to 0. And the opposite is little omega. These are the formal definitions that are useful for checking. They're not intuitive, though. So let me also give you the more pictorial, intuitive notion, which 90% of the time gives you the right answer, but you have to be careful that there are some corner cases where it doesn't work. F is O of g is essentially the same as a version of f is less than g. And theta would be something like similar or equal, and omega would be greater or equal. But f is less than g up to constant factors and for sufficiently large n. So if I take my function f, it might do some weird things for a while, but then there's a cutoff point from which on it behaves more stably. So that if I take my function g and multiply it by some constant number, it stays above the function f, right? That's what the definition says, and you can check how that matches the quotient limit and so on if you want. I'll come back to that example. For theta, it's basically combining two things. You can sandwich your function f between function g multiplied by a small constant and function g multiplied by a bigger constant. And again, before a certain threshold, the functions can do whatever, but after that, they stay in the right order. Okay? So morally, you should think whenever you read f is O of g, you want to read this is smaller. F is smaller than g. But with the caveat that it might be only up to constant factors and only for sufficiently large n. Okay? We could have a little fun with that example. Maybe let's skip this. You can look at the slides. Don't use plots like these for finite n to decide asymptotics. You can horribly be mistaken. And there's a nice example that I dug out years ago just to illustrate that point. Not so relevant for now. Let's see if that has sunk in. And let me go back to the picture. So well, if you're hardcore, you want to see the definitions, right? It's fun to watch the little bars go up and down. I know you can't see it, but right, in the interest of time, let's move on. Here's that. I'll comment on it a bit. Again, resist the urge to change your answer now. It's not really not gaining you anything. So answer B is what is essentially the right thing. If f is O of g, again, think of this as essentially meaning f is less or equal g. And that means g is bigger than f. Now, again, remember, what do the quotes mean? The quotes mean up to constant factors and only for sufficiently large n. Those two things you have to keep in mind. But because we're doing this on both sides, it works out like this. Now, there's something to be said for the last point, but that's a nitpick. If function f is identically 0, then you get trouble with the definitions by dividing by 0 and so on. But that's, we won't deal with so many algorithms that have cost 0 straight out for all inputs. So it's, mathematically speaking, this is only true if f is not exactly 0, the 0 function that is 0 at every point. Why did I present you the definition with the quotients? Because after all, that's, if you want to check asymptotics, the easiest way to do it. So let's have a few small examples on how you use this. So this first example, okay, has two statements. Let's pick this statement. This longer function is supposed to be in asymptotically equivalent to this smaller function. So we have a large function that's called f of n, and we have this one, let's call that g of n. So the first claim is that f of n is asymptotically equivalent to g of n. So if you look back to the definition, I'm not going to do it because I know it by heart, but you can go back. What you should check is that the limit of the two functions should converge to 1 when n goes to infinity. So how can we check that? The long form of this would be that. Now I'll insert f and g again. 20n cubed, 10 ln 10 ln n plus 5. That's a fraction with the sum in the numerator, so we split it. We have 20 over 20n cubed over 20n cubed. That's otherwise known as 1. And then we have these other two. N ln n over 20n cubed. Now for this last one is maybe obvious without thinking. We have a constant and divide by something that gets bigger and bigger and bigger. So that's 0. For that one, you may have to think a bit harder, so we can cancel a few things. Here it's also still easy. We can cancel 1n with 1n. And log n is less than n. So we can upper bound it by, so let me do this in small. We can say this is less than 10 divided 20n, because log n is less than n for large enough n. And so again, we have something that goes to 0. There's other ways to do it. If you have the quotient of two functions and both go to infinity, you can use L'Hopital's rule, which means take the derivative of the numerator divided by the derivative of the denominator, and then take the limit of that. If you keep doing that a few times for all polynomials and logarithms, that will resolve to the answer. Now, I also respect the comment at the bottom here. But this module is not an analysis class, so I'm fine if you use Wolfram Alpha to compute limits. I'm not really here to teach you limits. It would be useful if you were able to compute a few simple limits, just because I think it's common knowledge that is useful to know. But if you have to use that. Now, we can use the same calculation to also do this second part.
Why it is theta over there, theta of n cube? Because of Schreiber notation.
Well, I haven't explained that part. So so far we've only shown this part, the black claim. If we also want to prove this one, theta of n cubed, one direction. So first of all, this means two things. It means f is O of this one, and omega of this one. For the first part, we have to show that f divided n cubed stays bounded. And we've proven that it converges to 1. So it is asymptotically less than 1. Right, so we've shown that it converges to 1. And that means it is bounded. There's an upper limit you can put on the value of that thing. And that already implies the first statement. Now for the second statement, we have to invert the two roles. But luckily, we can use essentially the same statement. If that converges to 1, that converges to the reciprocal, and that's still 1. So it also means that this is bounded. And that implies the second claim. Let's do this example as well, at least part of it. So again, what do we have to do? We have to take the quotient of the two functions. And now you need to know the logarithm rules to work that one out. If there's an exponent inside the log, you can pull it out as a factor. And I have to divide that by log n. And now here I've done some nasty things. What does log mean without this LG? LG will always mean log with base 2 in our context. And inside the big O, it doesn't matter what the base is as long as it's any constant. Because all the logarithms differ just by a constant factor if the base is different, if the base is a constant. So we might as well put a 2 here as well. And then you can do the same trick. You can cancel the log on that one. And this one, log is less than log. So it converges to something less than 1. So in this case, it converges. The quotient is 6 if you pick log base 2 here. And so again, by showing that the quotient converges to a constant, you've shown that this divided this is upper bounded, and also the reciprocal, this divided by this, is bounded. And though that way you've proven both ways for theta. So if we call this f again, and this g, and that's all we had to prove. The last example doesn't even need a computation. It's just pointing out some idiosyncrasies of these definitions. That's a humongous number, probably about the size of the universe in some measures. The number of protons in the universe is probably less than that. But it's still a constant, so it's O of 1, because if you divide 10 to the 100 divided by 1. That's still bounded by 10 to the 100. So again, if you have two functions and you want to check some statement like this, you take the quotient and compute the limit. You compute the limit either using tools like Wolfram Alpha or the analysis 1 knowledge you learned either in high school or at some university class. We don't really need any fancy limits. Most of the limits can be dealt with the simple rules that you have learned there. But it's not the main skill I want to check. I want you to apply the definition and conclude the right things. Good. Let's do one more wake-up call. Well, we're almost done for this unit. There's two little things I want to point out, two little other things, little features of these asymptotic notations. One is in this question. I'll wait till 80 people have voted. All right. So there you go. In past cohorts, it was almost equal, but this time you've done pretty well. But quite a few people also said no. So why is it true that this function is in theta of n squared? Well, there's actually nothing really weird to do. You do the same as we did before. You take the first function, you divide it by the function in the parentheses, and you study the limit of this. Right, so obviously we cancel the n squared. So what's left is not a constant fact, is not a number. It's still something that depends on n. That's why the definition doesn't say quotient converges to a number. It says stays bounded. Famously, sign is between -1 and 1, so it's at most 1, right? So this whole thing is at most 3. And okay, here it also becomes relevant for the first time. If you remember, the definition took the quotient and then the absolute value, just to make sure that in case things go negative, positive, we don't get into trouble. But that's all we need to show. So that means the von implication, sine n plus 2 n squared is big O of n squared. And for the other direction, we have to take the other quotient. So because in this case we don't have a straight limit, we have to do both, at least in your head. All right, so we again cancel. Maybe could have skipped. This time we again want to bound. It's a fraction and we want to upper bound the fraction. That means we have to lower bound the denominator. Sine is always at least -1/2. So if I put in -1 here, I get an upper bound. Let's do this slow. -1 plus 2. And that's 1. Okay. So also the reciprocal, the other quotient, taking that function divided by that one, is also upper bounded. That the function itself fluctuates doesn't matter. Good. That was caveat number 1. This is basically just for you as a cheat sheet. There's a few rules. All of those are fairly obvious if you go back to the quotient. if you have some function and you multiply it by a constant, that's still within the same theta class, because you just make the fraction, the quotient, constant bigger, but it's still bounded if it was bounded before. More interesting, if you take the sum of two functions, that's the same theta class as the maximum of the two. Again, you can bound the sum as 2 times the maximum, and so on. You will discuss in more detail in the tutorials examples on how different functions relate. These are kind of named classes of function growths that often occur in algorithms. So that's why I listed them here. Otherwise, there's nothing special about them. Now I want to finish with one concrete example from analyzing an actual algorithm and seeing how the asymptotic notations might help to express things in a clearer way. What you see on the right is an algorithm to compute some number to the mth power, where m is an integer. Now, of course, there's many ways to do this, and the algorithm is somewhat smart, but it doesn't matter so much what it does. But it computes this without doing all the m multiplications. It does this by repeated squaring. But to make it work with any number m, you have to do some trickery. Again, as I said, this is not really so important. This is actual Python code. That's one way to get a list of the binary digits of a number in Python. Ignore this kind of weird stuff. That's Python specifics. But you can do this. If you have a number, you get a list of the digits in the binary representation of the number. Then you start with 1, and then you iterate through all the bits. You always do a multiplication, and if the bit is 1, you do another multiplication. That's the algorithm. OK, fine. How fast is it? Let's count the number of multiplications. OK, so there's one multiplication happening in line 6 and one happening in line 8. I guess these line numbers have moved. So this should be line 6. This should be line 8. The overall cost, if we have these conventions for the input, so the number of bits in m is n. Then we have exactly n operations here, because that loop is run through n times. And then the other one, we don't know exactly how many times, but if we have the number of ones in the binary representation of n, then we know. That's just a bit unwieldy. But it's obvious from this that it's at least n and at most 2n. OK? Question. From what we've shown here, what can we say about this algorithm? I want to stress here that we're after the most precise statement that you can make. So there are many correct answers to what you can say about C, but I want you to be as precise as possible without lying. All right, I think you can see, right? I didn't show it, yeah. I mean, just because it has the biggest blob doesn't mean it's correct, right? And yes, I know Slider supports smileys and emojis. Oh, someone found out how to type a square root. Oh, you copied it from... No, I didn't put it here. Fair to say that we have different answers. The most precise one, yeah, I know, this is deteriorating now, so I'll let you have fun. But I'll move on. It's getting late, I know. So the most precise statement you can make is theta n, because you can both prove the upper and lower bound. So let's briefly go through why c of n. We have this function c of n. Now we divide it by n. We don't really know what c of n is. There's a plot which, oh my god, looks a bit crazy, right? It's not a nice function, but you can still upper bound this by the 2n that we've had. So that quotient is bounded by 2. Fine. And I take the other quotient, n divided c of n. Then again, I upper bound this time using the lower bound for c. It's very similar to the sine example we've seen before, except that here there's not even a hope of specifying what c looks like precisely in primitive terms. But as I can say, this is at most 1 because c is at least n. So I've proven both of the quotients are bounded. Hence, the function is in theta of n. And I can't make a more precise statement with the notions we've had. I can't easily say a tilde statement unless I have some more concise way to express the function. And of course, you can express this in terms of m if you substitute that back in. So my last point from this is what's in the box down here. Usually, it's good enough to think of theta like tilde with a constant that you don't care about. Right? So f is roughly g up to constant factors and for large enough n. But sometimes there is no single constant that makes this true. It might be a case where the function weirdly fluctuates between an upper and a lower limit. And you can still make this theta statement. But there's no single constant that you could stick to n that would make it asymptotically equivalent to f or c. All right, let's leave it with that. See you tomorrow in a few hours.